happening here is a trend reversal. That's what this candle means, right? It's a gravestone doji candle. It's typically found at the tops of rallies, and it spells trend reversal. Now, does this mean tomorrow there's going to be a trend reversal or the day after? No. In the bigger picture, trend reversal.
This is a pattern which was developing over the last 2 years. And what if I told you that right now, in that exact moment, after the breakout, we predicted
the Bitcoin ETF announcement, which occurred on the 10th of January 2024. So that's a 10-10 date, because 01 is also as above so below. So 10-10, we can see here 10-10 on the Phoenix. The Phoenix, as you know, is 91 in Chaldean. 9 plus 1 equals 10, right? So of course it was released on a 10 date. So this proves that the Phoenix is clearly referring to Bitcoin.
Everybody, welcome to another live stream on Bitcoin faculty. We have officially completed all our basics in Python. We are moving on to more advanced concepts, but before we do that, we are already, and you will see a video uploaded later on tonight, we're already preparing to get our first certificate on the foundations of Python. So if you'd like to be a part of that, hit the like and subscribe. There's plenty more coming. For now, I'm going to switch over to our screen. So today we're looking at Numpy Arrays. We are on learnpython.org. The link is in the video description. Just going to also prep ChatGPT so long. It's definitely getting onto harder stuff, so I have a feeling we're going to need it. Also, I'll just show you guys now. This is how much progress we have made. If you look at that, we're actually basically halfway through to all the tutorials that are offered on learnpython.org, which is actually pretty awesome. And we did that in just 17 hours. So I see the code is not loading. See, we got a like. Thank you. Numpy Arrays. Always third time lucky. Okay, let's get started. Numpy arrays are great alternatives to Python lists. So we've done lists. Some of the key advantages of Numpy arrays are that they are fast, easy to work with, and give users the opportunity to perform calculations across entire arrays. In the following example, you will create two Python lists. Then you will import the numpy package and create numpy arrays out of the newly created lists. So in yesterday's video, we learned how to import libraries. So let's see what's actually going on here. So we have two lists, and they are basically height and weight. Remember, with our list, we use the square brackets, and these are all floating numbers, so they're basically decimal numbers. Then in the second step, we have imported the numpy library, and it looks like we've given it the name np. And then we are saying np height. So now we're creating, by the looks of it, two arrays from height and weight. We start by creating a variable, so np height and np weight. Then we assign two values, which in this case will be two arrays. So we basically say np dot array, and in the brackets we put what we want. So for the np height variable, we put in height in the brackets, and in the weight variable we put in weight. So notice here dot array, that seems to be how we take np, which is basically numpy. We've imported it as np, and we basically create an array. And remember, within that, we are taking the height and the weight. So if we run this code, let's see what happens. So we probably have to print it out. Should we try? Let's say print np underscore height and print np underscore weight. Still looks like a list to me. Okay, we'll come back to that. Print out the type of np height. So remember, we use the type function to identify what type of variable we're working with. Is it an integer? Is it a floating number? Is it a string? So to do that, we would say print, and then in brackets, remember everything in print is in brackets. So then we would say type, and then within type, we're trying to see what is the type of np height. And let's just, while we at it, look at the type of np weight. So it says np height is not defined. I don't think it's supposed to be doing this on the website. Should we try it up here where everything has been defined? So let's say print type np height, and then print type NP weights. Right? Yeah. So it says class numpy ND array. Remember, ND is our numpy library. Notice they're both the same. So numpy.ndArray. But there was also something else I want to. Oh, yeah. Remember, we did classes. We did classes and objects. Okay, so maybe just go and do some revision on that. From what I recall, a class is a bigger group of an object. So within your class, you can have multiple functions, objects. So let's see here. So this didn't work because it's not defined, but it worked up here, I presume. Print at the top. Okay, we've done that. Element-wise calculations. Now we can perform element-wise calculations on weight and height. For example, you could take all 6 of the height and weight observations above and calculate the BMI for each observation with a single equation. These operations are very fast and computationally efficient. They are particularly helpful when you have thousands of observations in your data. So if we want to calculate the BMI, first we create a variable called BMI. Remember to use descriptive variables. And basically we're going to take NP weight divided by NP height, and we're going to times it by 2. Or no, not times it, then we raise it to the power of 2. And if I recall correctly, based on order of operations, it will do the height to the power of 2 first. But I do stand to be corrected. So now we're going to try and print BMI and see what is the results that we get. So of course it's saying NP weight is not defined, so we're going to do it up here where we've defined everything. So we're going to say BMI equals NP weight divided by NP height to the power of 2. And then we're going to print our BMI. So let's go ahead and run that code. I really don't want to refresh this. Anybody there? Looks like I'm going to have to, okay, it's waking up. So name error, aha, we typed height wrong. So that's another thing you'll notice about variables. Well, in this case, it's saying it's not defined. It's not defined because I spelled it wrong. So NP height is defined. And there we go. It's done the calculations for us. Subsetting. Another great feature of Numpy Arrays is the ability to subset. For instance, if you wanted to know which observations in our BMI array are above 23, we could quickly subset it to find out. That's interesting. So BMI greater than 23 So we're trying to get a Boolean response. Is it true or is it false? And then we basically say BMI, we use square brackets, and BMI must be greater than 23. BMI is not defined. So let's go do that up here. So we're going to say BMI greater than 23, and then we're going to say BMI square brackets, BMI greater than 23. And then I would think we have to print it. No, it just did it. They all are above 23. And that's it. So I'm going to get some more information on this. So it seems like they're making a comparison here to lists. So why are numpy arrays better than lists, and how do they differ? So numpy arrays offer several advantages over Python lists, particularly in terms of performance, functionality, and ease of use when handling numerical data. Here are some of the key differences and benefits. Homogeneity, that's a big word. Numpy arrays, they are homogeneous, meaning all elements must be of the same type, usually numerical types like int or float. This uniformity allows for more efficient storage and operations. So when we take notes, I must just make mention of that. So we recall that when we were doing Python lists, that they could contain elements of different types. So you could create a list and you could have numbers, you could have strings, you could mix up integers and floating numbers. So in that sense, lists were more flexible. So I suppose it depends on your use case. If you're needing to do math calculations, it seems like numpy arrays are the way to go. So they're also good for memory efficiency. Numpy arrays use a contiguous block of memory, making them more memory efficient and faster for numerical computations. Python lists are essentially arrays of pointers to objects, which can lead to greater memory overhead and slower access times. Performance. Numpy arrays are optimized for numerical operations, maths in other words, and can perform element-wise operations in a vectorized manner. You know what? ChatGPT is just in another mood today. Can you please explain this simply? You are using big technical terms. Vectorized. I mean, really? I think this is better, but now it's like way too basic. Now they've just said numpy arrays use memory more efficiently. Anyway, let's move on. So Python lists use more memory because they store extra information about each item. Numpy arrays naturally, I suppose, are therefore much faster for doing maths with numbers. Python lists are slower because they are not designed for it. Yeah, I suppose lists have a different purpose if they can take different types of variables or values, variable types. Built-in tools. Numpy arrays come with many built-in tools for maths, statistics, and more. Python lists have fewer built-in tools for these kind of tasks. Working with parts of data, so Numpy arrays are easy to work with slices or chunks of the data. Python lists can also slice data but with fewer features. And then handling different sizes. So Numpy arrays can do math with arrays of different sizes automatically. Python lists need extra steps to do the same thing. So I suppose maybe like in your first list, you would have like maybe 10 items and your second list maybe 2. Maybe your maths calculation only needs the 2 in the second list. So Numpy arrays are a convenient way of working around that, I suppose, with less code. So the benefits of Numpy arrays are that they are quicker for number crunching. They come with more tools for working with numbers. They are easy to use. They make complex math simpler and code easier to read. They work well with other popular data tools. And then we've got an example here. So let's just see up here. Is there an explanation? No. So I see we've used range. List, range, size. We know that size is this number here. Start time equals time dot time. Yep, I think ChatGPT is just not getting me today. For once, Learn Python org's example is actually easier. So just to go over this again, we have height, weights. These are two lists. Then we need to import Numpy. Did they import it here? Using Numpy? Nope. Okay, so we have to import it because it's basically a library. Then we create two new variables that are basically using the dot array going to become an array. Don't forget we defined height here. I suppose because even though it still looked like a list, but now all the functionalities of Numpy arrays are enabled since we have applied array to the library, to Numpy with specific reference to the list. Then we check the type. It says an ND array. And then we did a maths calculation. And then lastly, we did subsetting. So I'm going to ask ChatGPT Because it says here that Numpy arrays come with many built-in tools. So we don't seem to be getting much information on that from learnpython.org. So let's do some research. What are these tools? Numpy comes with many built-in tools that make working with numerical data easier and more efficient. So mathematical functions, you can do all sorts of mathematical operations like addition, subtraction, multiplication, and division directly on arrays. So np.add array1, array2, or simply array1 plus array2. Okay. Statistical functions. That's interesting. Numpy provides functions to calculate statistical measures like mean, median, standard deviation, and variance. So I'll make notes of all of these functions. Linear algebra. It includes functions for matrix multiplication, determinants, and I can't say that word, eigenvalues, and solving linear equations. For example, np dot, matrix 1, matrix 2. Okay, we haven't come across that yet. Random number generation. You can generate random numbers or samples from different distributions. For example, np.random.rand 3, 3 for a 3 by 3 array of random numbers between 0 and 1. And also np.random.randint. Remember, int is for integer, and then we've specified 0, 10, and then size equals 5 for 5 random integers between 0 and 10. That could be quite useful. Reshaping and resizing. Numpy allows you to reshape arrays without changing their data. So we would say array.reshape 3, 4, and then to change a 1D array of 12 elements into a 3 by 4 2D array. You can perform operations on each element of the array. So np.sqrt, which stands for square root, would get the square root of each element. Aggregations. Numpy provides functions to sum up elements, find the minimum and maximum, and more. This is great. Actually, I love arrays. np.sum, np.min, np.max. We're going to test these. Logical operations. You can perform logical operations like comparison. So np greater array1, array2 to compare elements, or np.equal to check for equality. Advanced indexing to access part of arrays easily. So remember, indexing, we use square brackets. So we have array, then our square brackets 1, 3. To get a slice of the array, so remember, it includes 1 on the index. On the index, we always start at 0. So it would be the second character if it's a string. And then we would stop at 3, but 3 is exclusive. So we would actually stop at 2. That would be to get a slice of the array. Or otherwise, we could say array, and then this was our last example. Array greater than 5 to get elements greater than 5. So basically, this example here, subsetting, is basically indexing and slicing. Then we have Fourier transforms. Tools to perform Fourier transforms which are useful in signal processing. Example, np.fft.fft array for the fast Fourier transform. Handling missing data. Functions to handle or detect missing values. Example, np.isNan array to detect nans. That stands for not a number. Or np.nan to num array to replace nans with 0. Nan to num. So the 2 is quite important there. Broadcasting allows for operations on arrays of different shapes. For example, adding a 1D array to a 2D array without explicitly reshaping it. These tools make Numpy a powerful library for data manipulation, analysis, and scientific computing. So I'd like to actually test some of these on our example. So we have NP height. So let's say we want to add, or let's do this. Let's say print NP height plus NP weight. And it should give us the sum. Did it do it? I think it might have. Let me check on my phone with my calculator. It looks like it did. So if we go to calculate, we say 1.87 plus 81.65. Yeah. So there, we've learned now, well, we can see now how easy it is to just add them up. Then we can work out the mean. So we could say print np dot mean and in brackets np height to get the average height. So the average height is 1.87. Should we check it? Let's see here. So 1.87 plus 1.87 plus 1.82 plus 1.91 plus 1.9 plus 1.85. I want to check something. I want to say print print len of NP height. Because I mean, practically, imagine if that was like 1,000. Are we going to count them all? No. So we know it's 6. 1, 2, 3, 4, 5, 6. So now we just divide that by 6. Yep. And the answer is 1.87. So that's how we can work out a mean. Let's say we wanted to work out, although it seems like a silly calculation, but we could we could work out NPW and bet you can't choose and trying to think of a variable name. We will say weight plus height. Weight height equals NP weight plus NP height. So I've created a variable, right, called weight height. Let's work out the mean of weight height. So NP dot mean weight height. And it's worked it out for us. We can also work out the median, the standard, the variance, standard deviation. Yeah. Okay, linear algebra. I have a question which I'll ask ChatGPT just now about linear algebra. I don't want to get sidetracked now. Random number generation. You can generate random numbers from different distributions. Random dot rand. Let's see. NP height dot rand. What if we just leave it empty? I don't want to be specific. Will it generate? No. Okay. I said rand. So what's the function here? Random. Is it random or rand? I would think it's rand because of the int here. Anyway, there's reshaping and resizing. Not, I think for purposes of Bitcoin, we're not concerned with 2D and 1D models. Elements-wise operations. So we could calculate the square roots. So we could say print, what would we say? NP height dot sqrt. No, we would say NP dot sqrt, and then we would take the NP height, for example. Let's run. So it's calculated the square root of all the heights. Interesting. We can even get the exponentials. Let's find the minimum heights and or maybe the maximum heights. So we'll say, the reason why it's saying NP, okay, like NP dot mean, NP dot square roots, is remember we've imported our Numpy array as NP. So we would say print NP dot max NP height. And it looks like our answer is 1,91, and that is correct. So that's quite useful. we can also do logical operations to compare elements. So like we'll know, so we know none of these will be equal, although there are quite a few here in the heights that are equal, so we can try that out. We can say np dot equal, or print np dot equal on the np heights. So basically it looks like you can't compare within one variable. There needs to be two variables for it to compare to, in which case it should be false. Because I think if somebody weighs one kilogram, that's scary. False. So that's, remember, logical operators are Boolean, so they can either be true or false. Then in the example that they gave us, which was basically this over here, subsetting, where we also, I guess, here we were looking for BMI response, but remember, that's similar to what we just did now. In order to print it, it seems quite straightforward. So let's say, because we know our average height is 1.87, let's see, perhaps, can we do that? Array. So we could say, suppose you'd have to say, why is it doing this? NP height greater than 1.87, and then we can just say NP height, square brackets, NP height greater than 1.87. Not sure if that's going to work. Yeah, it did work. There's two, 1.91 and 1.9. Interesting. Fourier transforms. No idea what that would be. Let's make a note of that. And then having missing data. So, I mean, we don't, I think, have an issue with isNaN. We can try. We can say, friends, let's see if it's true or false, isNaN. And then NP heights. isNaN not defined. NP dot. I forgot NP. NP. Always refer to the Numpy array. So it's false. They're all numbers. And then you can NaN to number to replace nans with 0. Great. So that was actually quite fascinating. How far are we? Oh, okay. I see we're on cue for our short 10-minute break. I'll see you guys in 10 minutes.
what we see happening here is a trend reversal. That's what this candle means, right? It's a gravestone doji candle. It's typically found at the tops of rallies, and it spells trend reversal. Now, does this mean tomorrow there's going to be a trend reversal or the day after? No. In the bigger picture, trend reversal.
This is a pattern which was developing over the last 2 years. And what if I told you that right now, in that exact moment, after the breakout, we predicted
the Bitcoin ETF announcement, which occurred on the 10th of January 2024. So that's a 10-10 date, because 01 is also as above, so below. So 10-10, we can see here 10-10 on the Phoenix. The Phoenix, as you know, is 91 in Chaldean. 9 plus 1 equals 10, right? So of course it was released on a 10 date. So this proves that the Phoenix is clearly referring to Bitcoin.
I am back. Okay. So we've looked at the different types of functions within Numpy Arrays, or call it built-in tools. So, and we've practiced a few of them. Let's see the exercise. What we need to do is convert the list of weights from a list to a Numpy array. Then convert all of the weights from kilograms to pounds. Use the scalar conversion of 2.2 lbs per kilogram to make your conversion. Lastly, print the resulting array of weights in pounds. So it looks like currently the weights are in kilograms. It's one list. So I see they've imported Numpy for us. So we're going to create a new variable, and I think we call it NP. Yeah, we would say NP underscore weights underscore LBS equals, then we would say, I think we would say NP, we would say weight kg. Let's just check here. No, so we always NP weight. Hang on. We need to create two Numpy arrays from, okay, so we need to create the array after we need to convert it to an array. So to do that, we would say np.array. So let's do that first. Create a Numpy array. Yeah. So we would say np weight underscore kg equals np.array. Remember, we're saying np because we're calling on the Numpy library, and we would say weight kg. So we've created now an array. Then we, underneath here, this code goes here. So we're going to do the formula to convert the weight in kilograms to lbs. To do that, we're going to say np weight kg, and we're going to times it by 2.2. And then I think we just print np weight lbs. Let's see. And we got it right. So the one step we forgot is to import. Okay, that was done. We just forgot to convert it to an array. So don't forget to do that. You just create a new variable name, and then just remember you would say np.array, and then whatever your list name is, or the variable name for your list, your existing list, you put that in the bracket. Now it becomes array. And then we create whatever formula we need to, and that would be under a new variable name. And now it's quite easy because now we only have to refer to this variable name. So that's it. We've done Numpy arrays. However, I did just want to explore a few more things here. So let's just see here. Linear algebra. I remember when we looked at the very start of the series, we looked at programming in Bitcoin. And one of the things was one of the graphs that we need to use. I can't remember what it's called now, but I wonder if that uses linear algebra. So does Bitcoin mathematically use linear algebra? Yeah, there we go. It uses the elliptic curve. So we are going to get to that later on in this series. We're going to get to all the maths behind Bitcoin, but let's just read it. So it says Bitcoin as a cryptocurrency and a system does not directly use linear algebra in its core mathematical operations. However, it does involve various mathematical concepts, primarily centered around cryptography. So here are the key mathematical aspects of Bitcoin. So we have, oh, there's 3. So we need to make a note of this for when we get to our maths section, which will be after we've covered Python at an intermediary level. So we've got the elliptic curve cryptography, which that one I've read about. Then we have hash functions and Merkle trees. So just to briefly summarize, Bitcoin uses elliptic curve cryptography, specifically the SECP 256K1 curve, for its public key cryptography. This involves complex mathematical operations on elliptic curves, but it's not linear algebra. It's more about modular arithmetic and finite fields. So I will be finding sources on these: modular arithmetic and finite fields. Then hash functions. Bitcoin relies heavily on cryptographic hash functions, so SHA-256 for creating the hash of transactions and blocks. Hash functions are not related to linear algebra but are crucial for security and integrity. And then Merkle trees are used to efficiently and securely verify the integrity of large sets of data. Again, this involves hashing and tree data structures rather than linear algebra. While Bitcoin itself doesn't use linear algebra directly, some cryptographic systems and protocols might use linear algebra for various purposes, such as error correction codes, lattice-based cryptography, or some advanced cryptographic protocols. Here's what linear algebra might come into play in broader cryptographic contexts. So error correction codes. So this is where linear algebra is used in designing codes that can detect and correct errors in data transmission. We have lattice-based cryptography. Some post-quantum cryptographic algorithms use lattice problems, which involve linear algebra. Interesting. And then we have homomorphic encryption. In certain advanced encryption techniques, linear algebra operations are performed on encrypted data. To summarize, Bitcoin itself does not use linear algebra in its core operations. Its mathematical foundation is built on elliptic curve cryptography and hash functions, which do not involve linear algebra. However, linear algebra is used in other areas of cryptography and data science. Great, thank you. With regard to hashes above, does that essentially refer to hexadecimals? So we've are going to get, as I say, into elliptic curves. Okay, so not exactly. So remember when we covered hexadecimals, it's more of just a way of, I think formatting is the wrong word, but it's the way that data is represented, or specifically hashes, because hashes are probably in computer language are very long numbers, and so they are then converted to hexadecimals. It does say here though that hashes and hexadecimals are related, but refer to different concepts. So let's just wait for it to load. So a hash is a fixed size string or number that is generated from input data of any size using a hash function. Hash functions are designed to be fast and to produce a unique output for each unique input. Although collisions, different inputs producing the same hash can theoretically occur, they are rare if the hash function is good. Still just waiting for this. I don't know why it's being so slow now. In the context of Bitcoin, hash functions like SHA-256 are used. These hash functions take an input, like a transaction or block of transactions, and produce a fixed size string, usually represented in hexadecimal format. So hexadecimal or hex is a base 16 number system that uses 16 symbols, 0 to 9 to represent values 0 to 9 and A to F to represent values 10 to 15. It's a more compact way of representing binary data and is commonly used in computing because it aligns nicely with byte boundaries. So a byte is 8 bits and a hex digit represents 4 bits. So what would be represented in 8 numbers can effectively be reduced to 2. The output of a hash function is typically a binary string. For ease of reading and use, this binary string is often converted into a hexadecimal representation. For example, the SHA-256 hash function outputs a 256-bit or a 32-byte hash. When converted to hexadecimal, this results in a 64-character string. So we've reduced it from 64 bits or 256 numbers, to 64. So that's the greatness of hexadecimal. And you can see here in this example, input hello world hash binary. I don't know if that's a conversion to binary. Yeah. Anyway, we've covered that quite a bit in our hexadecimals. So what else was there? There was something else I wanted to check. We did random number generation. Again, I'm not concerned with 1D and 2D aspects. let's ask ChatGPT what is the use of Fourier transforms. Fourier transforms are mathematical tools used to analyze and process signals, and they have a wide range of applications in various fields. Here are some of key uses of Fourier transforms. Oh, so Fourier transforms decompose a signal into its constituent frequencies. This helps in understanding the frequency components of signals like audio, radio waves, and other types of waves. They help in designing filters that can remove unwanted noise or specific frequency components from a signal. Also, image processing. Techniques like JPEG compression use Fourier transforms to reduce the size of image files, and also for image filtering. So Fourier transforms are used to enhance or detect features in images. And then audio processing. So formats like MP3 use Fourier transforms to compress audio files by analyzing the frequency content and removing inaudible parts. So we can actually see how a lot of our apps today probably use this. It's used over communication channels. For physics and engineering, Fourier transforms are used to study the vibrational modes of structures and materials. Wow. Even medical imaging. Magnetic resonance imaging uses Fourier transforms to reconstruct images of the inside of the body from raw data collected by the MRI scanner, even CT scans like X-rays. Economics and finance. Time series analysis. Analyzing financial data to identify periodicities, trends, and cycles in economic indicators and stock prices. Astronomy. Analyzing signals from space to detect and study astronomical objects. So that is quite fascinating, where we've learned, or we can actually see the practical use, especially in the field of science and engineering and imagery and sound and the medical field, the use of Fourier transforms in a simple program like Python. So this looks quite complicated. I'm not going to go into that too much. But now we know why the Numpy array is actually quite important for those fields. Handling missing data, broadcasting. So I'm quite happy with our understanding, and I think we can move on to our notes just to prepare a summary. So I will now switch over our screens, and then we will be wrapping up this session. So today we learned about Numpy arrays. basically they are an alternative to lists. Keeping in mind that lists can contain all types of variable types. It can contain a mix of integers, floating point numbers, and even strings. Typically, the main case of a numpy use case of a numpy array is to keep it strictly to numbers, and we don't mix, so it's one type of number. They are specifically designed to be fast and easy to work with. Okay. Especially when it comes to mathematical computations. So what typically happens, I'm going to open a new slide here. Is that you will have two lists or one list. One list is also fine. And it will contain, sorry, it's a comma, a list. And we want to convert that to a numpy array. But first, we need to import the numpy package. So it's not actually a library, it's more like a numpy package. So we would say, it seems like there's a word for it, not consensus, but the trend is to say import numpy, and then generally we would say as np, so basically numpy package. So that's the first step. Then the second step is to basically create numpy arrays, a numpy array of this list. So we would say np underscore x, and then we would say equals np dot array. np refers to this. The dot array is the feature to basically convert x into an array. From there, now that it's converted into an array, going forward, we can use np.x and basically do whatever we want within the context of an array. And we learned what those different capabilities are. So now I'm just going to check out my ChatGPT. So for example, if we had np height and np weight, let's assume already these were lists that have been converted into arrays. Well, now we can simply say print, this is to get an output in the console, np, I'm just going to refer to it as h plus npw. So now we can quite simply add them together, or we can work out the mean. So let's say we want to work out some, basically we want to work out the mean. So what we did, or what we can do, is we can work out the mean of NP height. So we can say print, and then we say NP dot mean, and then in brackets NP H. We can even check the length of NPH. We can check out the median. So that would be NP dot median, and then whatever your variable is of the median that you want to check. We can do the standard deviation, so NP dot STD, and we can do the variance, so NP dot bar. So those are the math or the statistical functions that we would use. So we've looked at the mathematical, like in this instance, this is mathematical. These would be more statistical use cases. So these are things that would either be slower to do in a list or more difficult, like you would have to add in extra lines of code. Because remember, a list is based on indexing. A numpy, I can just check it quickly. Yeah, anyway, there was something about indexes. We can see that indexes are not really applying here. Okay, the linear algebra, I think, is beyond our reach at this point. We learned that we can create random number generation. We can do reshaping and resizing, and we can even calculate the square root. So we can say NP P dot SQRT, and whatever the name is, keeping in mind whatever this name is must be already, you must do your NP dot array and then the name of your list. We can also use it to check the minimum or maximum in a list. So we can say NP dot min and then NP height. So we did that to work out what was the maximum height, I think. So what else? We also can do logical operations, in other words, like check booleans. So we would say NP, we want to see greater. And then we want to see if NPH is greater than, sorry, not no greater than. So greater is the keyword here, dot greater, and then NP weight, and it's going to basically compare the two and determine if true or false. We can even check if they are equal by saying np.equal. Remember, for a Boolean, you need to compare two values, okay? So in this case, we couldn't just put NPH, we have to compare it to weight. Otherwise, how's Python going to determine what's true or false? We also, for example, we could look for elements, for example, greater than any example we did. Let me just check here. Oh, it was further down. So we basically said NPH, right, greater than, and I think our mean was at 1.87. And then basically to print that, we use square brackets, and then we say NPH greater than 1.87. And it's going to print all the values in here, in this list, or this array. It's going to tell us which ones are greater than 1.87. So this is where we create a Boolean, and then this is how we create the output. We also learned about Fourier transforms, how useful they are within the medical field, the scientific field, images, and even audio and communications. We can also check if an array has not a number or NaN. So NPH, and we can also then, if there are, we can say, sorry, and we have to say is NaN, not just NaN, is NaN. We can also then convert those NaNs to numbers. So we would say np dot NaN to num. And it will basically convert any NaNs to 0. That's it. Let me just switch over. So I feel like, well, I know this can feel like a lot to take in. So as we get to the more advanced sections, like today, we're going now onto an intermediary level. We're probably only going to be fitting in one section per session. I'm live every day at this time. Otherwise, my videos are available in the playlist, which you'll find on my channel. And yeah, just also remember that we starting revision on the basics that we've done. And that will also just help you become more and more familiar with what's happening as we repeat the concepts, and yeah, it will get easier. Repetition is always key to memory, but also to understanding. So I will see you guys tomorrow this time, or I'll see you in the next video if you're watching this as a series. The revisions are also going to be available in the series, and you will see that I have colored those thumbnails with green, so you can quite easily pick up those videos if you want to specifically do revision on the basics. Have a good evening or day wherever you are, and see you in the next video.